The problem asks you if radius grows, then how much does area grow? And so we find this by looking at the change in r. That's the symbol change. And the average quantity of a change is taken by this, the average change of a, the change of a per unit time, because r is changing by time. So if we look over here, this is the area of a circle is equal to pi r squared. And so we can note that r is changing by time, t, and a is proportional to r squared. So we have to use what's called the derivative, which is basically this, but instead of being an average, it's a specific change in time, because we'll find that the change of area changes over time. So we take the derivative of a, which is like saying what's the change in a per time, and we find the change per time of pi r squared, because that's what a is. And so we find that by taking the derivative, we get 2 pi r times the change in r per time, which by the way is known and constant. We know how much the radius of the circle is changing, and we're trying to find the rate of the area changing. Okay, so then we come down here, we get a solution. The change in area per time is 2 pi r times the rate of r changing per time. So we kind of get a little bit of an interesting result. If r is 1, so at the time where r equals 1, then the change in area is just 2 pi times the rate of r changing. And if r is 2, then it grows, it doubles up, goes from 2 to 4. So we can see that as r goes to infinity, as it grows, so does the rate of change in the area, proportional to 2 pi. So then I have this other case where if we let the change of rate in r per time is 1, let's say this is a meter wide and it changes a meter every second, then we could say this is 1 meter per second. And so then we find that the change in area per time is equal to 2 pi r. Interestingly, that's the circumference of a circle. But anyway, so then we can graph it. What we find, if I graph a equals 2 pi r, I get this graph where we have a and we have r, and that should be dA. That should be the change in a per r. We have this line, very straight, and that's because this is just a regular r. It's not r squared or anything. And so this is the line we get where dr is equal to 1. If it's greater than 1, then it gets a little bit higher, so area grows faster. And if it's less than 1, then area goes slower. And this line down here would be if rate of r changing was 0.